Such a wonderful idea for a lecture series. And thank you all for listening wherever you are. So today I was instructed to sort of give my own personal connection to recent developments in climate science. And so I'm going to give you a very narrow perspective, mainly based on work that I've been involved with. And I'm keeping this as a very broad talk because I understand that the audience may have very different backgrounds. So I'm trying to just paint you an overview picture of this particular topic. So I really want to emphasize these new perspectives that we have now on the role of internal variability in regional climate change and climate model evaluation. So at the heart of this topic, of course, is that we are living in a time now when anthropogenic climate change is very much emerging, but it is emerging against a background of internal climate variability. And this leads to some challenging research frontiers that, of course, have been studied for a long time. In particular, how do we disentangle these dual influences on regional and local climate, anthropogenic versus internal or natural variability? And I will define what I mean by internal variability in a moment. And then this also brings up the challenge of how do we assess our climate models at these local and regional scales, given this background noise, if you will, from internal variability. And these are outstanding challenges that have been there for a long time in all of the IPCC assessment reports. They're now part of the grand challenges with the WCRP program. So we're still very much as a community actively addressing these questions. So my particular focus in this talk and what I have brought, I think, to the field is this notion of initial condition large ensembles. And that's going to really be the framework for what I will be talking to you about today. So outline of the rest of the talk, I'll spend a few moments briefly defining in broad terms what we mean by internal climate variability. And then that will set the stage for how to make sense of climate model projections, and in particular, projections that are done in this large ensemble framework. And then you'll see then the challenges that arise when we try to interpret trends in the real world and try to parse them between anthropogenic versus internal influences. And then this also has a lot of implications for how our strategies for evaluating our models, our climate models. And then finally, I'll leave you with some brief big picture summary and outlook, and then some further reading resources and tools that you might find useful. So internal climate variability is ubiquitous on all time and space scales, and it arises primarily through these three components of the climate system, although I should say I have omitted land atmosphere interactions, which actually I think is becoming an important part of this story, but I'm not going to speak about that here today. So internal climate variability, that's simply the spontaneously generated variability in our climate system that is unforced. So it does not depend on any external radiative forcing, for example, volcanic eruptions or changes in the solar cycle, that kind of thing. It happens due to just the internal dynamics in the climate system. And it can originate just from atmospheric processes, and this is a big one for climate. It can also originate from coupled interactions between the ocean and the atmosphere. And then finally, there is intrinsic variability in the ocean, and that can then have an imprint on the climate system. So if we begin first with the atmosphere, as we are all, of course, very familiar with over our lives, weather variability. So we always think of this as sort of a high frequency component of the climate system, day-to-day and week-to-week variability. It's largely caused, at least in the extratropics, by variations in the shape and strength of the jet stream, as you see here in this image for February of 2015. And I love this example because for the US, we had record warmth in the western part of the US and record cold in the east during this month, and really polarized, if I may say, the country in many ways, not only in terms of weather. And these are very large scale patterns, and they are caused just by intrinsic jet stream dynamics, or they can be caused just by intrinsic jet stream dynamics. But the important thing here is that they have very large spatial scales. It's not noise in the sense of, one location versus another, but it's really these broad scale, continental scale patterns that arise from these planetary waves in the jet stream. So the predictability, of course, of these types of jet stream variations is, only on the order of weeks, and it's limited by the intrinsic nonlinear dynamics of the fluid. And the important thing here is that it is not confined to high frequencies, but really this nonlinear chaotic system, or can be modeled as a random stochastic process, produces sort of a white noise or slightly red noise continuum of variability, which means that it actually has an imprint on longer time scales, including decadal and centennial. And this is a really important part of the background level of variability in the climate system. And I think sometimes we forget that the atmosphere can do a lot of damage, even on these longer timescales. So then we can move on, of course, to other familiar sources of internal variability, and that is the coupled interactions between the ocean and the atmosphere. And these give rise to this sort of alphabet soup here, if you will, of phenomena, all the way from the 30 to 60 day timescale Madden-Julian oscillation in the tropics, to the interannual ENSO phenomenon, to the decadal and multi-decadal variability that exists in the Pacific and the Atlantic sectors. And again, what is important here is that or at least for the purpose of my presentation, is this notion of the predictability time horizon. For ENSO, we're now actually getting longer predictability time, up to 2 years, particularly for the cold La Nina phase of ENSO. And the dynamics of this predictability are really becoming well understood. For the Pacific and Atlantic decadal, multi-decadal oscillations, even though they have these sort of long time scales, as you can tell by their naming, the predictability time is actually quite short, at least as we understand it up to now. So up to about a decade, roughly speaking, for the AMO, and for the PDO, it's even less than that. So there's a real sort of threshold of predictability for these phenomena. And then finally, the ocean intrinsic variability, I'll just mention it. I'm not going to talk about it further. But of course, there are very energetic mesoscale eddies, sort of akin to the jet stream variability, if you will, in the atmosphere. And then there are the very slow circulations, for example, the Atlantic thermohaline circulation, which can be triggered, variability in that can be triggered by sort of stochastic atmospheric forcing. So, as I said, as I've been emphasizing, the predictability time horizon of this internal variability, whether it has its origin in the atmosphere or in the coupled ocean-atmosphere interactions, is weeks to a decade. There's a recent summary here in this JGR paper by Williams et al. And so really, you can think of this internal variability as a roll of the dice once you get beyond that predictability time scale. So it truly is a random, unpredictable occurrence once you get beyond that time scale. And the important point here is that it introduces unavoidable uncertainty into climate model projections, particularly at these local and regional scales. And that's sort of been a theme of my work for a long time. I'll just point you to a recent paper in Earth's Future that sort of summarizes this point. So it's unavoidable. It's sort of a certain uncertainty, if you will, that we understand. It's not that we don't understand this uncertain source of uncertainty. We do. And it is very important to take that into account for all kinds of issues in terms of where the climate system is headed. So now, with that brief introduction, I'm now going to turn to this notion of initial condition large ensembles, because I think the community has found them very insightful, as I say, for many purposes. And it's really a very active part of climate science research right now. So I and my co-convener, Keith Rogers, we co-convened a working group of the US CLIVAR program that just finished its 3-year term. And as part of the working group activities, we wrote this perspective in Nature Climate Change that came out about a year ago, trying to give a very comprehensive view of what types of insights one can gain from these initial condition large ensembles and future prospects for how the community might come together in terms of coordinating these types of experiments with climate models. So if you're interested in sort of a very broad brush discussion, I would point you to this paper. So I will show you some results from one of these large so-called initial condition large ensembles, the one that I'm most familiar with because I helped to spearhead it. And that is the one with the NCAR Community Earth System Model version 1. We now have a version 2 large ensemble that's almost ready for release. And this is a global, fully coupled model, as all of these types of initial condition large ensembles are. And this one happens to be at about a 1 degree spatial resolution. And the reference paper is Kay et al. In 2015. So I'd like to go through with you the design of these large ensembles so you can appreciate their value and also understand how to interpret them. So the CSM1 Large Ensemble Project, what is it? Well, it's a set of simulations with one climate model and one scenario of external radiative forcing. and as follows. So we began, as you see with this green line here, with a control simulation of this fully coupled climate model. It has an ocean and atmosphere, a cryosphere, biology, atmospheric chemistry to some extent. And we ran this model for about 400 years under constant pre-industrial year 1850 radiative conditions. So the model spins up, comes into sort of a quasi-equilibrium, and produces its own internal variability, for example, ENSO events or Atlantic multi-decadal variability, that sort of thing. And this model, I should say, has been deemed to be one of the absolute top models in terms of its representation of internal variability amongst all of the world's climate models. And then once the model sort of reaches its own quasi-steady state, if you will, including internal variability, we then prescribe the sequence of historical, and then in the future, following the business as usual RCP 8.5 radiative forcing protocols. So this would mean that we are prescribing the known changes in volcanoes, in the solar cycle, in the buildup of greenhouse gases. I'm sure I'm forgetting some things, but the usual anthropogenic and natural external radiative forcing. And then we run this first simulation in this blue arrow here, all the way out to 2100. So it's the typical kind of climate experiments that are used for all of the IPCC reports. So what is new here is that we decided not to stick with one simulation, but we had resources to run 40. There's nothing special about that number. It is not biblical, as I like to say. It's just what we had resources for. And what we did was on January 1st of 1920, we applied a very small perturbation to the atmospheric temperatures on the order of 10 to the minus 14 degree Kelvin. So this is truly the butterfly effect, or the level of round off error in the atmospheric temperatures in the model. So it really is an imperceptible perturbation to the initial conditions. And importantly, the ocean, the ice, and the land initial states are identical for each of these 40 simulations. And the only perturbation is this tiny one in the atmosphere. So then we run all 40 of these. So I call this the butterfly effect, or if you will, coming back to this notion of the roll of the dice, that once you get beyond this predictability timescale, roughly a decade, the spread in these simulations is not predictable. So you're getting both this combination of the anthropogenic or the forced component of change, and you're getting the internal variability, which plays out differently in each of these simulations. So the sequence of El Nino events, the sequence of Atlantic multi-decadal variability is different in each of these simulations, because it's a random process, if you will, and it's not tied to anything that we've prescribed in the forcing. So now I will show you what really opened our eyes when we first ran these simulations. And these are, I call them postage stamp maps. They look like little postage stamps. But these are, I'm just zooming in here over over North America, so Canada and the US. And what you're looking at here are the first 30 simulations. It was just easier to fit 30 on a page, for how the model simulates wintertime air temperature in the colors and the sea level pressure in contours trends over the past 50 years, roughly, when we did this study from 1963 to 2012. So these are 50-year trends in the recent past. And you can look at the different, you can see the numbers here in each of these little panels, all the way from 1 to 30. And you can see that they are very much not the same. You can have cooling in Canada in some of the simulations, and warming in Canada in others. There's a huge variety of expressions of these trends. And this tells you right away that the forced component, largely anthropogenic, driven by greenhouse gases, is small compared to the internal variability, even for a trend that is 50 years in length. So this has so many implications, and I just will talk about some of those as we go through. So again, the reason why each one of these is different is because of this roll of the dice of the internal variability. The hammer, which is my icon for the external radiative forcing, is the same in each one of these simulations, and the model is the same. So the only reason that they can be different is this roll of the dice of the internal variability. So we can do very simple arithmetic and to estimate, try to isolate and estimate what the forced component is of these trends. We simply take the arithmetic average of all 40 simulations, and that is shown in this box with the dark outline here on the bottom, the ensemble mean, or EM. So that is what our best estimate here is of the forced component, largely driven by the rise in greenhouse gases for North America, for wintertime air temperatures and the sea level pressure. And so what you see is actually a very simple pattern, more a poleward amplified pattern of warming, strongest near the Arctic region of Canada, and smallest as you go south into Mexico. And then the other thing you notice is that there are very few contours on here, even though the contouring and the coloring is the same in all the panels. So this tells you that the forced component of the atmospheric circulation trend is negligible. Yeah, that's what it tells you. So then we can look at the observed trend. So that's shown in this green box here. And that's what the observed trends look like. And you can see there's a lot of contours on there, a lot of circulation trend. And you can see that the pattern of warming has some similarity with the forced pattern according to the model, but also some difference. And if you look through this set of 30 simulations, you can actually, if you just go up, I know you can't see my cursor, but ensemble member 12 here, the third on the right-hand side, looks a lot like the observations. So again, the model can give you what the real world did, but it can also give you something different. And that tells you that the real world, if the model is credible in its internal variability and its forced response, the real world didn't have to look like what it looks like. And I'll make that point a little bit later in the talk as well. Okay, so future changes. The important thing here is that we should expect a range of outcomes under the combined influence of anthropogenic forcing and internal variability. So I'll just show you one example from this recent paper for projected trends in wintertime precipitation over the next 50 years, again from the CESM1 large ensemble. So now I'm just going to boil it down to a couple of maps. So this is the anthropogenic influence, which we determined by averaging all 40 simulations. So it's projected, as in many models, to get wetter over most of North America, with the exception of Mexico. And the largest increase in precipitation is projected along the west coast of North America, and then also along the eastern seaboard of the US. So that's not necessarily what we will get because of this introduction of the randomness of the internal variability. So here on the bottom, I'm showing you sort of the two kind of, think of this as the 5th to 95th percentile probability maps from this set of 40 simulations. So I'm showing you on the left, the one that had the, that overall for North America as a whole had the second most largest increase in precipitation. And the one on the right is the member that had the second smallest increase or driest trend overall for the continent. So by taking the second N members of these 40 members, I'm roughly spanning the 5th to 95th percentile across the ensemble. And you can see that they look really different. And, you know, one of them will tell us that California is going to be really wet in the future. And the other one tells us actually there's going to be a modest drying trend. And both of those are plausible. And I like to sort of use this in the US, we have an author, Mark Twain, who is often quoted, and I'm sort of adapting his euphemism here. So I like to think of the anthropogenic influence as sort of what we expect if we only think about how human activity will impact the climate system. And then I like to think about that actually what we get, what we will get is this combined influence of anthropogenic and internal variability, and that can very much modify the picture. And we really don't know where we will land in the real world between this, these two bottom maps. So we should always keep in our minds that it's a range of outcomes that we should expect that are both equally plausible and do not negate at all the existence of anthropogenic climate change. I think that's just a really important point to communicate to the public. So this leads us then to the notion of the risk of climate change. And here I'm speaking directly about the risk that comes from this addition of the internal variability, which is not predictable more than, you know, a few years in advance, how that combines with the anthropogenic influence. So coming back to our example of winter precipitation over the US, this is a slightly older study, but the results, I think, are not going to be much different with a newer model. So this is, I'll walk you through the plot, but this is the chance of having a positive trend in wintertime precipitation over the next 50 years. So we simply find the number of simulations at each grid box that had an increase in precipitation over this next 50 years. And we divide that number by the total number of simulations, which is 40, and that gives us this percentage. And so, for example, over Canada, we have a very strong probability of having a greater than 85% chance of having wetter winters due to this combined superposition of internal influence and anthropogenic. On the west coast of the US, there's a 65% chance of drier winters. So, you know, a little bit better than even chances, but it's not 80%. And then in the eastern 2/3 of the US, there's actually equal chances, wet and dry. So these chances are all very consistent with the with the anthropogenic influence, but the way that the internal variability can either augment or offset the anthropogenic influence then leads to these probabilities. So then this leads me to a very important application of these large ensembles, and that is how should we understand and interpret the coupled model intercomparison archives. So these CMIP archives that I'm sure many of you have used in your research. It's sort of the backbone for all of the IPCC assessment reports. And these are, over the different generations of CMIP. We now have CMIP 3, 5, and 6. Now we have at least 40 models, I think, in the most recent CMIP exercise. And most of them only have a few simulations. So then it becomes tricky to assess whether models are truly structurally different, meaning each model has a different formulation, or to some extent. It may have different representations of the physics in the climate system. Certainly it has different ways of parameterizing unresolved processes, different numbers of vertical levels in the atmosphere and the ocean, different spatial resolution, different computing architecture, etc. So this, of course, will cause structural differences between the models, but it may be hard to tell whether models are truly structurally different if the sampling of the internal variability is inadequate due to the only having a few simulations. So let me illustrate that a little bit more concretely here. Again, this is from a little bit older work, but the results, I think, are still true. So this is from CMIP 5. So here I'm showing you, I've color shaded here the wintertime sea level pressure trends for the next 50 years. So I'm always using this 50-year period just as my example. And I've taken the first 9 models. I'm not telling you what they are. I've simply taken them in alphabetical order of their names. So there's no cherry picking here. And this is what those trends look like. And you can see that they all look pretty different from one another. I'll just point out a few regions. So this is the North Atlantic European sector, where Model 3 and Model 5 have very sort of almost opposite trends from each other. And I should say this is one simulation for each of these models. It was just the first simulation if the model provided more than one. We can also look here in the North Pacific and find models, again, that have completely opposite trends. And we can even look at the high latitudes of the Southern Hemisphere and find completely opposite trends. So the point is here, are these differences just due to the different random sequences of internal variability, or is it really truly a model structural difference? And you really cannot answer that question if you only have a few simulations of each model. So if you just let your eye remember these colors here, now I'll show you the first 9 simulations from the CESM1 large ensemble. And of course, by design, the differences in these trends amongst the different simulations can only be due to the different sequence of internal variability. So once again, you can see a lot of variation between the different simulations, very much like we saw with the CMIP archive. The North Atlantic oscillation, if you will, can have opposite sign in the different simulations of this model. The North Pacific can have opposite sea level pressure trends. and even the southern hemisphere high latitudes can be opposite. So this can only be due to the internal variability. So you can already see that it's hard to interpret the CMIP archive if you don't have enough simulations to really be able to estimate or to distinguish between the internal variability impact and the model structural impact. And then one can, of course, be much more sophisticated. And I'll give you some reference papers at the end if you're interested in more reading. But you can collapse all of these maps, and simply at each grid box, you can take the standard deviation of these trend maps for either the CSM1 large ensemble or the 38 models that contributed to CMIP5. And you can just look at, do an F-test to see whether they really are distinct from one another. And in this particular example, the high latitudes of the Northern Hemisphere, they are indistinguishable. So one might conclude from that the differences amongst the models in the CMIP archive in the Arctic and northern high latitudes is simply a result of internal variability, and there really is no model structural difference. Okay, so I'm coming towards the end of the talk, and I very much want to open it up to questions. So I think you can see from these examples that there's a real need, an important need for a multi-model large ensemble archive. And that's one of the things that our working group set out to kind of spearhead. And so in this perspective paper, we give you the URL of the existing large ensembles that exist with the CMIP5 and the CMIP6 models, where we deem it to be a large ensemble if it has at least 15 members. Again, there's a lot of literature that goes into how many members do you need, to really beat down the noise from the internal variability, and the answer very much depends on, your interest, the quantity of interest, and the time and space scale. Anyway, we've deemed it to be 15 members. So this is a resource, it's sort of one-stop shopping for these large ensembles that make it easy for you to get the data and really look at these. And then I'm going to wrap up with what I think is a crucial piece that still needs a lot of attention from the community, a lot more research. And that is this notion of an observationally based large ensemble. So as I hinted at the very beginning with those postage stamp maps, that the observed trends over North America are some combination of anthropogenic influence and internal variability. So what the real world could have actually looked different. It just gave us one of those sequences of internal variability. So I had a postdoc, Karen McKinnon, a few years ago, and her work was to construct an observationally based large ensemble. I don't have time to go into the details, obviously, but the idea is to take the instrumental data, air temperature, sea level pressure, precipitation, for example, and you preserve the statistical properties of the variability in those data, for example, the variance, the autocorrelation, and very importantly, the spatial patterns of variability. But you devise a method to randomly shuffle the data in time. And we can test our method. Another beauty of large ensembles is as a methodological test bed. So you can take the large ensemble where you know the full range of internal variability across the 40 members, and you can see how well your method works if you randomly shuffle the data in only one simulation and then compare it to the full spread. And we find actually the method works very well, sort of ballpark less than 20% error when we test it in this large ensemble framework. So the last figure here to show you is sort of opened my eyes. We call it a synthetic, if you will, observational large ensemble. So again, the last 50 years, these are the wintertime air temperature trends over North America. The top is actually what occurred. So we had a lot of warming over Western Canada and a little bit less warming over the US with a bit of an east-west contrast. So of course, as we know now, that is this combined effect of the sequence of internal variability and a forced response. And then what Karen did was she had 1,000 of these synthetic random shuffling of the observed data. And we picked out the 2.5th percentile and the 97.5th percentile of the warming as a whole over North America. So it's sort of the 95% range, if you will. And you can think of these as parallel worlds. So we could have had cooling over Western Canada or warming over Eastern Canada in the real world that would be consistent with an anthropogenic influence, but just due to a different sequence of internal variability. So it's very important to recognize this. So summary and outlook. Again, my remarks are directed at this intersection of anthropogenic climate change and internal variability. And there's been so much work on this topic now with large ensembles. And I just hope to, give you just a few illustrations. But the bottom line is that anthropogenic climate change may be very difficult to untangle from internal climate variability at local and regional scales, and that these initial condition large ensembles with fully coupled Earth system models provide a lot of new insights and understanding. I've only given you the tip of the iceberg in this short talk. I thought I could leave you with some further reading, just picking out two papers that are very broad, sort of introduction to this topic, and then you can drill down in the references to these papers. But the first is by Tell et al., and it's sort of gives you the theoretical sort of physics underpinnings of this idea of parallel worlds or parallel climate realizations. And then the paper that was led by our working group, the US CLIVAR working group. And then just to leave you also with some tools that are available. If you go to my website, you can get to this archive of large ensembles with CMIP 5 and CMIP 6 models. And we have a nice new tool developed in our group called the NCAR Climate Variability Diagnostics Package for large ensembles that does a lot of very nice computations for you. And I'm happy to answer any questions, and you're always welcome to email me. Thank you so much for your attention. Okay, I will end the show.
Okay, thank you, Clara. It was a very inspiring talk, and it really claims for questions. And indeed, we already have 9 questions in the box, so I will quickly start to read them. Please forgive me if I will spell your name wrongly, and I will do my best. So the first one is by Faranak Tunchi. Thanks for the nice talk. Considering the time dependence of certain hydroclimatic variables, can we deduce that the dependence of variables like precipitation and temperature is also dependent to spatial-temporal scale, meaning in certain scale the dependence is stronger while in others it is not?
Yes, thank you for the question. It's a very important point. Yes, the answer is that, the spatio-temporal scales are different for different variables in the climate system. And some have, more variability relative to forced influence, and some have less. And so it's not, you know, I've shown you examples for air temperature and precipitation, but the quantitative results may differ for other variables, for example, soil moisture or ocean heat content. These all have different, you know, amounts of inertia in them. And the other point that I forgot to make that's very important is that, of course, one can also aggregate the data across regions. So you can average all of North America together or average the globe together. And when you do that, of course, you diminish the influence of internal variability. And but of course, that doesn't help you when you are interested in these local and regional scales.
Okay, the next one is by Giorgio Graffino. It's understood that 400-year-long spin-up is enough to reach equilibrium in the atmosphere. How was the initialization done for the ocean components instead? Does it play a role in the simulations for decadal or longer timescales?
Thank you very much for the question. So that is discussed in detail in the K et al. Reference paper for the CSM1 large ensemble, and you can find that paper on my webpage. Before the coupled system was run for this 400-year control, there had already been a spin up. And for the ocean, I forget how long that was. So, you know, at NCAR, we have such a superb oceanography group that I can assure you they were looking very carefully to make sure that the ocean, you know, was reasonably spun up even before this 400-year segment of the control run. Certainly, the ocean initial condition, and in particular, the state of the AMOC, definitely, of course, imparts a degree of predictability, and we are actually starting to examine that in the new CSM2 large ensemble. But again, you know, I would say that at least from our results to date and other people looking at decadal prediction, that, you know, you'd be hard pressed to find predictability beyond about 10 years that is, you know, of substantial amplitude on the atmosphere.
Sorry. The next question is by Sergei Vasilkevich. Can we identify some persistent features in those 40 grand ensemble simulations, e.g. global temperature average, that are not subject to influence of internal variability?
Yes, absolutely. And I think I spoke to that earlier question. Yes, the larger the spatial scales that you average over, the more you will beat down the internal variability because you're sort of averaging, you know, patterns that have positive and negative anomalies. So of course, that's a very important, yes, we can. But, you know, if we really are interested in these local and regional scales, you know, we can't do that. And then, of course, there are very, you know, you'll have another talk, I think, in this series by Dr. Gabi Hegerl. And, you know, she's one of the pioneers on this formal detection and attribution methodologies to tease out the anthropogenic component from data. And that's, of course, another complementary approach to finding the anthropogenic component.
Okay, there are two questions by Gavin Schmidt. Maybe I will read the first one and then I will wait for your answer and then I will move on to the second one. What are the quantities issues that a large ensemble gives different results than just examining the PI control 50-year sequences?
Yes, thank you very much for that question, Gavin. So I guess there are maybe 2 points to address here. The first is whether anthropogenic, let's just say the rise in greenhouse gases, whether that in itself alters the characteristics of the internal variability. You know, there's some indication that maybe it will energize the hydrological cycle, you'll get more variability in precipitation. ENSO may change in terms of its amplitude and spatial pattern. So the characteristics of the internal variability could be have some forced component to it. I think to date, where we are now in terms of anthropogenic forcing, I think there's not a lot of evidence outside of the Arctic that the variability has a forced change. But I very much expect that as we continue, you know, to change, human activity continues to alter the climate system, that the variability will begin to change its character. And a postdoc of mine is actually looking at atmospheric modes of variability and how they change under climate change. So you won't be able to get that from a pre-industrial control run. And then the second thing is, I agree with you that to the extent that there are not any substantial changes in the internal variability, you could use 50-year segments from a long pre-industrial control run to, you know, get additional samples of trends. And we've done that actually. It's a way of augmenting, if you will, the ensemble size for these large ensembles. But it will never, the point also of these large ensembles is not just to sample the internal variability, but it's also to obtain the forced response on these local scales. And that, of course, a pre-industrial control run doesn't give you.
And then the second question was, the CMIP multimodal ensemble has broader variation than just atmospheric variations. Different ensemble members also select from ocean state variations. What does this imply for your comparison of the large ensemble to CMIP?
Yeah, another active area of research. So in the CSM1 large ensemble, we only perturb the atmospheric initial condition. There's work, that one might expect that if you also sample across a range of ocean initial conditions, that you might get even larger spread. And I think that's still active area of research. We've designed the new CSM2 large ensemble, which will be released in mid-June. I'm happy to send whatever email list this group has. I'd be happy to announce that. I can send that to Valerio when it's ready. But we purposefully designed the CSM2 large ensemble to sample different AMOC initial states with enough ensemble members that you can really untangle the impact of ocean initial condition uncertainty on the spread, versus atmospheric initial condition uncertainty on the spread. So again, I'm expecting the results will depend very much on your quantity of interest, what variable you're interested in. If it's within the ocean or high up in the atmosphere, it may give a different answer. But certainly one would expect that within the time frame that the ocean has an effect on the atmosphere, one might expect more spread if you sample across different ocean initial conditions. But once you're beyond that time scale, then my thinking is that you're sort of just in the climate attractor, and it didn't matter really what state you began from.
Okay, it's 5:30, so I would suggest that we do not take on any more questions, and if Clara is okay with that, I will try to read the remaining ones. Okay, then there's one by Maybridge Schillinger. Thanks, this was super interesting. You only perturbed the initial state. Could you perturb some forcing value or some model parameters as well? Would you expect some similar results?
Yeah, certainly that is a sort of complementary angle. And there's a whole effort that's called perturbed physics ensembles, where the uncertainty, as you rightly point out, a lot of the parameterizations, in addition to the forcings, for example, aerosols, anthropogenic aerosols, these are not well known, and there is uncertainty in them. And so then if you produce an ensemble where you perturb the parameters in the model, that can, of course, also then, analogous to this initial condition ensemble, give you spread. And that is very important. I guess to some extent, one hopes that the CMIP archive spans that parameter space, but of course it doesn't. It's not big enough to do that. And then the forcing, as you point out, we don't, even for the observed estimates, for example, of anthropogenic aerosols, and biomass burning, for example, of course, we don't have complete knowledge of those. And so that introduces uncertainty. And then, of course, society and the choices that it makes in the coming years and decades, that also then will introduce this forcing or scenario uncertainty. So those are very important points. Thank you.
There's Winda Falconer. Thanks for the great talk. How would you communicate the effect of internal variability as seen in the large ensembles and the uncertainty in the word we get to the wider public and policymakers?
Yeah, such a good question. Thank you for asking it. So I just have a very direct and simple answer. And when I give public talks, this is what I emphasize. That I emphasize that this word uncertainty is, not to be misinterpreted. And that's why I've started to use the term certain uncertainty. That's what I titled my Earth's Future paper that came out this past year, that we know a lot about internal climate variability. We know a lot about the mechanisms of ENSO, the mechanisms that underlie the Atlantic multi-decadal oscillation. And there's a lot we don't know, but there's a lot that we know. And we know a lot about what limits the predictability of that internal variability. So we have a lot of knowledge about internal variability, and then we have a lot of knowledge then about how it can mask or obscure anthropogenic signals. And we shouldn't be surprised if, for example, I'll use North America, as my example. If the east coast of North America gets colder in the future in the wintertime, and there are more snowstorms or whatever, that does not negate the presence and influence of human-induced climate change. It's completely expected. That's why I try to use this range of outcomes when I frame my public talks, that anthropogenic signal is there, but we should, on these local scales, also be cognizant of the role of internal variability. In the tropics, the internal variability compared to the anthropogenic response, at least in terms of temperature, is much smaller. So there, that range of outcomes narrows and more towards the anthropogenic influence. So that's how I just very, clearly frame that, I think we've done ourselves a disservice a little bit in the IPCC, in the past IPCC reports, by just showing these single maps of the human-induced part of climate change, which is fine, and it's important to understand the physics behind that. But that doesn't mean that that's what the real world, that's what you will see, or that's what will happen in the coming decades. Rather, it's this range of possibility that will happen. And as we go further and further into the future, we will, if we don't clean up our act, we will more and more see the anthropogenic influence. And we have to act now, obviously, to avoid that. So thank you.
There are still a number of questions, so please let us know if we have to stop at some point.
No, I'm good. It's the morning for me, so.
Christian Zdanovic, is the range of natural variability predicted to increase as the world warms up? And if so, does that not kill any hope of ever being able to reliably anticipate the effects of the external forcings at the regional scale?
Okay, yeah, that's a very nice way to frame the question. We've already talked about it a little bit, but I think overall, actually, we're learning from this new CSN2 large ensemble, which, by the way, has 100 members, just like the Max Planck Institute Grand Ensemble. And 100 members, you may think, that's overkill. But what it's really useful for, and it's a point that I actually wanted to make in my talk and I forgot, is that the extremes, right? We're of course, as a society, extreme events can be very damaging to the ecosystems and to, of course, society. And extreme events, by their nature, are rare, right? So they don't occur very often. So how do you get a good statistical sample of extreme events if you only have one simulation with a climate model, or even just a few? You don't, unless you do some other approaches. But these 100-member large ensembles, now all of a sudden you have a sample of extreme events from all 100. So you've increased your sample size by a factor of 100. You can now really study in a quantitative way how extreme events, the tails of the distributions, may change. And this is a really just a very open and exciting area of research. And a lot of people are starting to go into that. So I think we don't know the full answer by any means of how the variability and the extremes will change, although we have theoretical considerations of that. But I don't think the changes will be so extreme that they're going to mask the underlying change in the mean. So I think for the most part, the shift in the whole distribution with anthropogenic climate change, that will probably be the dominant influence. And then the change in the shape of the distribution, if there is any, that will be an additional effect. But I don't think it will be the dominant effect by and large.
Thierry Panduf, very nice talk, Clara, thanks. Recent ocean modeling studies have shown that intrinsic ocean variability is very weak without oceanic mesoscale, but strongly increases and reaches scales of several decades and several thousand kilometers when eddies are even partially resolved. Are we now able, perhaps through CSM2, to assess the impact of ocean model resolution on climate internal variability? If not, do you have a guess of whether CIV would change in structure intensity scales as mesoscale eddies are resolved?
Yeah, thank you, Thierry. I know we've talked about this in person a few years ago at the Large Ensembles workshop. Thank you. It's such an important point. Everything I've shown you today is based on a coarse, sort of eddy parameterized ocean model in the CSM. And I know that there are very exciting efforts in other modeling centers to incorporate, resolved mesoscales in the ocean, and that really can change even to first order, and maybe in the extratropics, the degree of influence that the ocean has, say, on the jet stream, for example. I think it's still, open area of research. So it may be that, I think these large ensembles were never, for example, the CSM2 large ensemble, it shares the same identical ocean component as the CSM1. So that particular comparison is not going to shed any light on this issue of the mesoscale ocean eddies. But it's a very good point. I guess it echoes Gavin Schmidt's point about the influence of that the ocean actually may cause even more spread in the climate system due to its intrinsic variability that may be increased if we include a representation of mesoscale eddies. So I can't really comment further. Thanks, though.
Simon Josie, very interesting talk, thanks. Could you comment on whether the level of internal variability differs strongly between models? And if so, is this a problem for establishing structural differences?
Such a great question, and I can comment a little bit. So it's such an important point that, models, obviously we know they have different climate sensitivities, or they can, and therefore they will have different amplitudes of the forced response. But the internal variability can also be structurally different between models. And it's really hard to assess that unless you have large ensembles, at least on the time scales that I've been emphasizing. So I would point you to our Nature Climate Change paper, the one that our working group did, led by myself in 2020. And then some follow-up paper led by a member of that working group and a former postdoc of mine, Flavio Lehner. And he has a new paper in Earth's Future, or late last year published, looking at this very question and actually showing sort of the Hawkins and Sutton type of diagrams for signal to noise and time of emergence, and how the structural differences in internal variability across models influences that answer. And the upshot is, yes, there are. You can discern significant differences in internal variability across models with these large ensembles. And in some cases, it's important, and in some cases, it's not very important. But this is something that now we can do. And then the other, I would say, more challenging aspect is, how do we evaluate internal variability in climate models given our short observational record? And that, we're very limited. And that's where these observational large ensembles come in. Karen McKinnon, whose work I highlighted in the talk, we've just submitted a new paper that sort of extends this observational large ensemble work to extremes in precipitation. And I think that's one way to get at a better way to evaluate climate models' internal variability. But we're always going to be, hampered by just the fact that, we don't have a long records in the real world. So we have a limited sampling of internal variability.
There's one question by Matt Collins. You mainly gave examples of mid-high latitudes where the signal-to-noise ratio seems quite low. What about the tropics? Is the signal-to-noise ratio larger there?
Yeah. So thank you, Matt. And so I have to make sure I have my the correct thinking here. So definitely it's a little paradoxical because, for example, in the Arctic, right, we have polar amplification of anthropogenic warming, and that's well established and understood. So you might expect that the signal to noise in the Arctic would be fairly high, but there's a lot of noise from internal variability at those high latitudes. So the signal to noise is actually quite small in the Arctic, despite the large signal. The tropics absolutely has, I think the tropics actually, now I got a little confused. Maybe I should be careful what I say, but in general, I think it has a higher signal to noise. Although, again, it's a little paradoxical because, of course, we have a lot of variability in the tropics as well, like coming from ENSO, et cetera. But overall, I think it's, such an ocean-dominated region that the signal to noise does tend to be higher. We do have signal to noise maps from these large ensembles that are global. I forget now if they're in that Nature Climate Change paper. I'm not sure they made it in there. But I certainly have, there are such maps for large ensembles. I'd be happy to follow up with you offline if you're interested.
Peter Haynes, a signal-to-noise paradox has been identified in seasonal forecasting, and one interpretation is that models overestimate internal variability relative to the real world. Do you have any views on this? In particular, what does the McKinnon and Dazer work tell us about this?
Yeah, so thank you, Peter. Nice to see you or hear you. I think this is a very important issue, this whole, possible signal to noise paradox, that models are better at forecasting themselves than they are at forecasting the real world. We don't know how ubiquitous that is. I think so far it's been demonstrated to be the case for the North Atlantic Oscillation, for example, in particular. If it really is a fundamental flaw of the climate models, globally or in all regions, then that it would imply that these large ensembles have too much noise from internal variability. However, and I'm glad that you brought up the work led by Karen McKinnon, the CESM1 large ensemble, and we have it documented in her papers, it is actually really good in its amplitude of internal variability. There are definitely exceptions. I think summertime air temperature variability over, the central part of the continents, the air is overestimated. That is much better now in the CSM2 large ensemble. I think it had to do with soil moisture parameterizations. So I still have a hard time reconciling the signal to noise paradox that's been demonstrated in this forecasting mode, and what we see, at least what I've seen in this evaluation of internal variability in the CSM1. So I don't know. I think it's a really important open question, what the implications are of the signal to noise paradox for large ensembles, and I don't know the answer yet.
One question by Shooting Yang. Thanks for the great talk. Could you comment on the WCRP WMO's Digital Twins project? Is the kilometer scale climate simulation sufficient to provide climate information, assuming it is not realistic to have large ensembles for kilometer scale climate simulations with current technology?
I have to say that I'm not up to speed on the Digital Twins project, but thank you for bringing it up so that I will become up to speed. But in terms of resolving, kilometer scale climate with models, I think the way to go probably with our resources, unless of course the ocean mesoscale, the importance of the ocean mesoscale variability really is paramount. A useful approach that people have taken, there are many nice studies out there now, is to take the some of the members of a coarse resolution fully coupled global climate model, and then to use that as the boundary conditions for a regional climate model. Some recent work of Daniel Swain has done that for the CSM1 large ensemble targeted on precipitation over the west coast of North America. And so I think that's a fruitful way to go forward to resolving the kilometer scale variability and the topographic influences, et cetera. But I think realistically to run enough members of a large ensemble with a kilometer scale type model globally is probably beyond the realm of possibility at this point anyway.
Shiwa Zhu, thanks for your great sharing. Parametric uncertainty has not been touched in CNIP. Could you please comment how that could impact the predictability and climate projections?
Great question, really not in my area of expertise. I know that Ben Sanderson and Laurent Terret, they are both at Cerfax in Toulouse, in France. They're exploring this issue. I happen to know them just as colleagues, but I'm sure there are many other groups that are looking at this, and I can't comment, but it's a very important point. Thank you.
Tron Iverson, thank you for a very clear and interesting presentation. In the talk, you mainly treated the role of internal variability in a statistical way. Do you have any comment as to what extent the ability to model different modes of internal variability would influence the evaluation of internal variability? And isn't the role of CNIP also to evaluate the model's ability to represent such modes as opposed to a single model ensemble?
Yeah, so we've touched on this already, but thank you again. Yes, and I mentioned at the very end of my talk, under the tools, this climate variability diagnostics package for large ensembles. Happy to follow up with you offline, but that's exactly what this diagnostics package that you as the user can apply to any set of model simulations and data, observational data. And we've done that. And actually we have a paper, I have a user's guide to that package where I explain all of that and show results from this multi-model large ensemble archive. And we have a paper published, led by John Fasulo in my group. I'm happy to send you that reference, where we actually evaluate the dominant modes of variability all the way from the NAO to ENSO to the PNA, kind of you name it, the top maybe 8 or 10 modes globally. And then we show how how the spread of these patterns and amplitudes of the modes, how they are influenced by the limited sampling of internal variability if you use a finite time period. So that's the spread across the members. And then we compare that with the CMIT models, one simulation per model. So you can really start to quantify the impact of, or to quantify whether models do have structural differences in how they represent these modes. And in some cases, you can identify a structural difference in the NAO, for example, and sometimes you can't. And I think that is just the way it is. But it's very eye-opening. You know, you may think, okay, a 60-year-long record or even longer of the NAO is enough to really define its pattern and amplitude. And it's surprising how, you know, the results vary across the ensemble members, even with a fixed record length of 60 years.
Okay, there's one last question. I'm sorry, Beniamino, maybe you might want to get in contact with Clara by email, but it's really late. David Gampe asks, thank you for the great and inspiring talk. My question goes in a similar direction as Christian's earlier. Variables with a strong force trend, such as air temperature, show an increased variability toward the end of this century. Could you maybe comment on how this affects the interpretation, or how and whether it should, in particular, of extremes and their change over the course of the next decades?
Yeah, if I understand the gist of your comment, that absolutely, I think, as you rightly point out, you know, that the distribution in a particular variable, for example, air temperature, may not just simply shift with climate change, but it may change its, you know, width or skewness or whatever, indicating a change in variability. And yes, both aspects absolutely are part of the force response and have to be taken into account as climate change proceeds and strengthens. So yeah, I agree, it's important. And that is one shortcoming at this stage of our observational large ensemble work, is that you cannot simply take the observed variability and put it onto a future mean state to look at the distribution, because the variability itself may change. So that's something, an important aspect to look at with models. Thank you all for such great questions. It's so nice to have a dialogue, or not quite a dialogue, with everyone.
Yeah, thank you, Clara, and yeah, it was great.